All right, hello, this is Mrs. Valdez again, and in this video we're going to work through the rest of the Chapter 4 practice test, and this will match up with Part 2 of the Chapter 4 test. In this example, or in these next three examples, it says you want an investment to triple in value with an interest rate of 6.8% per year. How many years will it take if it is compounded semi-annually, daily, and then continuously? So for the first two questions, we're going to use that the amount after time is the principal, and then it's times the quantity 1 plus rate divided by n to the power of nt. So that is if it says it's compounded daily, monthly, semi-annually, quarterly, etc. So for 20, if it's compounded semi-annually, we're going to use n equals 2. Okay, now if you want an investment to triple, I usually just make it really simple and say that your principal is $1, which I know is kind of silly, but it just makes the math easier. So I have $1 as my principal, and I want to invest that at 6%. So everywhere I see R, I'm going to plug in 0.068. And then it's going to be divided by 2 because that's our n value. And then that will be to the power of 2t. Now, if you want it to triple, your amount after time is going to be 3. So we're trying to solve this for t. We want to know how long this will take. All right. So the reason I use $1 right here is because, sure, you could divide by 1, but you don't really need to do that. At this point, the next thing you need to do is figure out what this decimal part is before you move on. And if you plug that in a calculator, that part will give you 1.034. So this is 3 equals 1.034 is this part that we get in parentheses here, and then that's to the power of 2t. So at this point, it's already an exponential, so we can change it into a log to solve for t. So now we have log with a base of 1.034 of 3 is equal to 2t. So now I would plug this part, the log part, into a calculator, and remember to do that, you're going to need to use this change of base formula. So we'll have the log of 3 divided by the log of 1.034 is equal to 2t. If you plug that in a calculator, you get about 32.8584 is equal to 2t. And then if you divide by 2, you will get, that looks like a Z. Divide by 2, you get 16.43 years for t. All right. So now let's see if that is different if we have our interest compounding daily. So in this example, daily means that we're going to have n equal 365. So I'm still going to suppose that I have $1 invested as my principal. But what's going to change in this problem is that where we have n, that will now be 365. So again, we're going to start by just plugging this part in the parentheses in our calculator. And if you do that, you get 1.00186301. Okay, so now I have 3 equals, you don't really need to worry about this 1 in front of the parentheses. So we'll just write that decimal part, 1.001863301. Oh, and I see I made a mistake here. This should be to the power of 365t, because now we're using n is 365. My mistake. Okay, so make sure you have 365t for that exponent. All right, and now at this point, we can change it into a log. So we have log with a base of 1.000186301 of 3 equals 365t. So if you plug in, we have to use that change of base formula again. So we'll have log of 3 divided by log of 1.000186301. That equals 365t. This number ends up being 5,897.51 equals 365t. And then lastly, we can divide by that 365. And if you do that, you get 16.16 years for t. So notice it does shorten up the time it takes to reach that tripled investment by about a quarter of a year. So maybe 3 months sooner, you'll have more money. All right, now let's see what the difference is if we look at continuous compounding. All right, so for this one, we have to figure out that we're using this other formula. So continuous compounding is that P times E to the power of RT. So again, we still want the investment to triple. We're still assuming we're investing $1 just because it makes the math easier. And then it's e to the power of 0.068t. All right, now this is already a log by itself. I mean, that 1 right there is not really necessary. So I'm actually going to erase it. It's easier to see that this is the ln of 3 equals 0.068t. If you plug that in your well, first we want to get t by itself. So what I would do is actually just divide by 0.068 right away. So these will cancel. And again, when you're doing this in a calculator, make sure you wrap up those parentheses around the 3. All right, and then if you solve that, you get t equals 16.616 years again. So notice it doesn't really make a difference whether you're compounding daily versus continuously. You still get the same amount of time. All right. So now let's look at a half-life problem. It says the half-life of radium is 1,600 years. How long will it take a 100-gram sample to decay to 17 grams? So with these half-life problems, your first step is always to calculate the rate, okay? And that is always using this formula where you take the ln of 2 divided by h, and h is your half-life. So in this example, we're going to do the ln of 2 divided by 1,600. Again, make sure you put parentheses around that. And when you do this, I keep as many decimal places as I can, and I usually just use everything that's in my calculator. So your rate is 0.000433217. So I know that feels like a lot of decimal places, but it makes your answer more accurate. So now we use our formula for calculating half-life, which is m of t equals m naught, which is your initial mass, times e to the power of RT. So if we fill in what we know, we want our sample to decay to 17 grams. So that's how much we will have. We started with 100, so that's m naught. E to the power of, and this is where we're going to put that big decimal, well, small decimal, but with a lot of decimal places. All right. And then that's times t. T is what we're trying to solve for. So first step is to isolate the e part. So we'll divide by 100. So we get 0.17 equals e to the power of 0.000433217t. Oh, and I notice again, This should actually be a negative exponent here because we're dealing with radioactive decay. So let's throw that negative on there. So otherwise we're going to get a very strange answer. All right, so let's change the form. This is a natural log of that 0.17 is equal to negative 0.000433217t. So now we can divide by that decimal. All right. Okay, here's the last time we have to write it. Okay, so these will cancel. If you plug that in your calculator, remember to close up that parenthesis, and you end up with about 4,090 years for your time. So that takes quite a long time. Okay, and if you forget that negative, you'll end up having a negative amount of years, so you'll know like you just forgot the negative when you divided. Okay. This last section switches gears because we start solving. So this was like section 4.4 material. For number 24, the first step you do when you're solving these exponential equations is isolate the exponential part. So in this one, we'll have to divide by 7. Then we get e to the power of x equals 71.42857. Okay, now we can change it to a log. So we have the natural log of 71.42857 is equal to x. And then if you plug the ln of that number into your calculator, you get 4.2687 is approximately equal to x. So notice in the directions it says round all answers to 4 decimal places. So we're going to do that for all of these problems. Okay, number 25 is very similar. We will start by getting the exponential part by itself. So first I need to subtract 6. Then I get 2 to the power of 3x equals 3,448. Now I can change it into a log. So this will be the log base 2 of 3,448 is equal to the exponent, which is 3x. All right. And then we'll have to use our change of base formula to figure this out. So this is log of 3,448 divided by a log of the base, which is 2, and that equals 3x. If you plug this in your calculator, it gives you 11.7515 is equal to 3x. And if you divide by 3, you will get 3.9172 is approximately equal to x. All right. Okay, let's look at number 26. So we did have a question very similar to number 26 on the homework. And there's a couple of different ways to do this problem. The way I do it is I take the log of both sides. So I'm going to take the log of 10 and then to the power of x plus 3 equals the log of 6 to the power of 2x minus 3. The reason I do that is because then what you can do is use that power property to bring that exponent to the front. So now your exponent, which has the variable in it, is no longer isolated or trapped in that exponent part. Okay, so for this one, the left-hand side is kind of nice because this log of 10, since we're using base 10, that's just 1. So this thing is just 1, so it kind of just doesn't really factor into our solving. This side, though, will have that 2x minus 3 times the log of 6, okay? Now, if you plug this into your calculator, this log of 6 part, that's going to give you about 0.7782. Okay, so here's what we've got. On this left side, we're just left with x plus 3 equals, and then we have this decimal 0.7782 times this quantity 2x minus 3. So now it's not a log problem anymore. Now this is just a straightforward equation where you get x by itself. All right, so the next thing that I'm going to do is distribute this 0.7782. So I end up with multiplying that by 2x gives you 1.5564x minus, when you multiply that by 3, you get 2.3346. Over here, we still have x plus 3. All right, so now I'm going to get everything, all my x's on one side, so I'm going to subtract this x here, and then subtract this 1x here, and then I'll do this at the same time. I'm going to add the 2.3346 over to this 3, plus 2.3346. So here my x cancels, here that 2.3346 cancels. And what I'm left with is 5.3346 equals 0.5564x. All right, so my last step then is just to divide by 0.5564. And if you do that, you'll end up with about 9.5877 for your x. All right. Okay, so the rest of this section is, well, we got 3 log equations, and then we have a couple of factoring equations. So first thing in 27, this one is pretty straightforward. You can go right into changing it into an exponential. So since there's a single log on this side, that's when you know you can change it into an exponential to solve for x. So this will be 3 to the power of 3 equals 2 minus x. So 3 to the power of 3 we know is 27. That equals 2 minus x. So now I'm going to subtract 2. So we end up with 25 equals negative x. So that means x is going to equal negative 25. All right, so since that one was an exact answer, we don't need to worry about rounding to 4 decimal places. All right, in 28, eventually we're going to change this into an exponential, but before we can do that, we need to condense this log part. And since these 2 logs are being added, we know that we're going to multiply the pieces inside of them. So this will be log base 4 of x times the quantity x minus 6 is equal to 2. All right, and now that that log part is by itself, we can change it to an exponential. So this will be 4 to the power of 2 equals x times x minus 6. All right, so now we just start solving. I would distribute this x into the parentheses and make this 16 equals x squared minus 6x. I can see that this is going to be a quadratic, so let's get 16 out of here. So we have 0 equals x squared minus 6x minus 16. And this actually is factorable. So you can think of 2 numbers that multiply to give you negative 16 and add to negative 6. Those are 2 and negative 8. So this is 0 equals x plus 2 times x minus 8, which gives you the solutions x equals negative 2 and x equals positive 8. Now, here's what you need to check. Sometimes those solutions might give you something that doesn't work. So if we look at this x equals negative 2, if you go back and plug it into this original equation, you're taking the log base 4 of negative 2. You cannot take logs of negative numbers. If you try to do that, it's going to give you a domain error. So this is not a real solution. It doesn't work. So the only one that does is 8, because if you go back and plug 8 into either part in that original equation, you can take the log base 4 of 8. You can take the log base 4 of 8 minus 6 because that's just the log base 4 of 2. So those are x equals 8 is the only solution that doesn't cause you to take a log of a negative number. So we don't use that -2 solution. You need to remember to only use the solution that works in the original equation. All right, let's try another problem. So again, first thing we need to do here is condense this into a single log. So we're going to do that with a subtraction problem. So this is going to turn into a division or a quotient. So we have log base 8 of x plus 5 over x minus 2 equals 1. Okay, and now the log part is all by itself, so we can change the form. So this is log to the power 8 to the power of 1 equals x plus 5 over x minus 2. So this is just 8. So at this point, I would multiply both sides by x minus 2 to get the x minus 2 out of the denominator on this side. And then we can distribute this 8. So we get 8x minus 16 equals x plus 5. All right, and from here we can just solve like we usually would. Let's subtract this x and add this 16. So we get these terms to cancel, and now we have 7x equals 21. So x equals 3. All right, and again, it's always a good idea to check, but if you plug 3 into here, you get 8, which you can take the log of that. If you plug 3 into here, you get 1, and you can take the log of that. So we're okay. All right, 30 and 31, we will need to use our factoring skills. So in 30, let's start by taking out some GCFs. So I noticed that both of these terms have an x in them. So let's take that out. And they also both have this e to the power of x in them. So let's take that out. Then what I'm left with is just an x minus 3. Now you actually have 3 pieces here. This first one is x. So this is just going to be x equals 0. Hey, that's one of your solutions. This next piece is e to the power of x equals 0. So this part is actually going to yield no solution because there's no exponent that you can plug in to get 0. So this part does not give us a solution. And then the x minus 3 factor is going to give us a solution of x equals 3. All right, so that is done. So we ended up with these 2 solutions, x equals 0 and x equals 3. All right, 31 we can actually factor like a quadratic. So we're going to go right into 2 numbers that multiply to -14 and add up to -5. So you can hopefully see that that is -7 and +2. So when we factor this, it's going to be e to the power of x minus 7 times e to the power of x plus 2 equals 0. All right, so if you set e to the power of x minus 7 equal to 0, that's going to give us our first solution. And then e to the x plus 2 equals 0 is the other piece. So for this one, it's e to the power of x equals 7. So to solve this, we'll change it to the natural log of 7 equals x. And if you plug the natural log of 7 in your calculator, you get about 1.9459 for your solution. In this other factor, you end up with e to the power of x equals -2. And remember, you can't ever have if you try to change this, it would be the ln of -2 equals x, and that is not going to give you a solution. All right, so we just have one solution for number 31. Okay, this last page is all about graphing logs. So if you have 3 different colors to use for number 32, that might be helpful. So the first graph we're going to create is y equals the natural log of x. And for this graph, we're going to start with changing it into an exponential. So remember, it's a base of e. So if I change this into an exponential, it's going to be e to the power of y is equal to x. So if we make a table of values, it's actually a lot easier to plug in numbers for y. Because at that point, we could just say like, okay, for this one, it's e to the power of negative 2. Just plug that in your calculator, and you get about 0.14. For this one, you plug in e to the power of negative 1. That gives you about 0.37. For this number, you plug in e to the power of 0. That gives you 1. E to the power of 1 gives you 2.72. And e squared gives you 7.39. So now we can just go ahead and plot those points. So the first ordered pair, I go over 0.14 down 2, and that's going to be pretty close to that y-axis. Then I go over 0.37 down 1, over 1 up 0, over 2.72 up 1, and then over 7.39 up 2. That's about right there. I think I might have graphed that in the wrong spot. Let me check. 1, 2, 3, 4, 5, 6, 7. I did. I was too far over. So there's 7.39 comma 2. So it goes straight down, and then it kind of starts to grow less quickly as you go to the right. So this is the graph of, let's see, y equals ln of x. Okay, the next graph I'm going to do is y equals the negative ln of x. And if you remember those transformations, that negative is just going to reflect over the x-axis. So we don't have to make a new table. We can just take these points that we did in the first one, flip them over the x-axis to get our new graph. For those points I'm graphing in green, you can see. So it goes straight up and then starts to level off as you go to the right. So this is the graph of y equals negative ln of x. And then our last graph is y equals ln of negative x, which this one is a reflection over the y-axis. So again, we'll go back to our original graph and we'll just reflect over the y-axis. We'll have these points that I'm graphing in red. And this one again is going to go straight down as you get closer to x equals 0 and then start to level off. This is y equals the ln of negative x. All right, so if you understand those transformations, you can use that parent graph to come up with your new graphs. All right, and then this last section, it says complete a table for each function and graph the functions on the same axis. So for 33, the first thing we're going to graph is y equals 1/2 to the power of x. So if you plug in y 1/2 to the power of negative 2, that's actually going to give you 4. 1/2 to the power of negative 1 is actually just the reciprocal, so that's 2. 1/2 to the power of 0 is 1. 1/2 to the power of 1 is 1/2. 1/2 to the power of 2 is 1/4. And 1/2 to the power of 3 is 1/8. Okay, now we can just actually go ahead and graph these right away. So I'm going to go left 2 up 4. So here's the first point for that graph. Left 1 up 2, 0, 1, 1, 1/2, 2, 1/4, and then 3, 1/8. So this, we can see, is an exponential decay. And I know it's decay because its base is 1/2. So remember, if it's got a base between 0 and 1, that means it's an exponential decay. And then I'm just going to label this. So this is y equals 1/2 to the power of x. All right, now I'm going to grab a second color. You don't need to do any work to graph y equals log base 1/2 of x, because this and this are just inverses of each other. So that means my x values now become my y values. So I'm going to use -2, -1, 0, 1, 2, 3. And my y values become my x values. 4, 2, 1, 1/2, 1/4, and 1/8. So if we graph these, the first point, you're going to go over 4, down 2. Then you're going to go over 2, down 1, over 1, up 0, over 1/2, up 1, over 1/4, up 2, and then over 1/8, up 3. So then this, right here, this blue graph, that is the graph of y equals log base 1/2 of x. And one thing to note, if you do this correctly, you should notice that these are a reflection over the line y equals x, and that's because they're just inverses of each other. So this is the line y equals x, and you can see that reflecting happening. All right, so we're going to use that graph here to answer some questions about the domain, range, and equation of the asymptote of each function. So the first function is the graph we created for 1/2 to the power of x. You can plug anything in for x. So the domain for that one is all reals. And then notice, I'm going to grab a highlighter here, that line levels off at y equals 0. So that is your asymptote, and it also relates to your range. The range is y is greater than 0, and then your asymptote is just y equals 0. Okay? For the log function, remember this is the inverse, so now your range is all reals. And then your domain is based on this line right here, because a log graph is always to the right of x equals 0. So your domain is x is greater than 0. Remember, you can only take logs of positive numbers. And then your asymptote is the line x equals 0. Okay, so now let's look at what happens in this third one. So this 3 out front is just going to make the graph steeper, but that does not, is a vertical stretch by a factor of 3, but that does not have any impact on your domain and range, okay? The things that are going to change domain and range are, first of all, this negative up here. That's like having a negative in front of the parentheses, and what that does is it reflects, so it's going to reflect over the y-axis, which if you think of reflecting that y equals 1/2 to the power of x-axis, it's still all going to be above the x-axis. So our range, that's not going to actually affect our range. This, however, will. This is going to move everything down too, including the asymptote. So the asymptote was at y equals 0. Now it's going to be at y equals -2. And that means your range is going to be y is greater than -2. Okay, your domain is still all reals. Now, one thing to note in this example is, if there happened to be a negative right here, that would make your range y is less than -2. Okay, because it would flip it over the x-axis, and now everything would be under the line y equals -2. So just keep that in mind. All right, And then our last example is looking at that log function. Let me grab one more color here. So this, just mentioned this, that negative out front is going to reflect over the x-axis. Okay, so like if you think of your log function, it's going to flip upside down. And then this is going to shift everything left 1 unit. So if you look at your graph of 1/2, the log of 1/2 of x, what's going to happen is it's going to like flip upside down. So it's going to be like this. But then it's also going to take and shift it to the left 1. Okay, so now your new asymptote is going to be x equals -1, which means your domain is now going to be all the x's greater than -1. All right, so it's still going to the right, which is why it's still greater than, and then your range, of course, is always. All right, so I hope that helped. If you have any questions, feel free to comment down below or come find me at school. All right.